Okay, so today we're going to focus on section 6.1, Euler's method, the second day. All right, we're going to look at linear approximations, and then we'll start with 6.2, differential equations, growth and decay. So the first thing we're going to do is look at Euler's method. All right, and what Euler's method does is it uses linear approximations to solve differential equations. So for instance, if I want to find the y value when x equals a certain value, okay, I can use Euler's approximation to do so. All right, so I'm going to kind of break it up, and it's going to make more sense when we get into this first example here. So here's some notation that we need to talk about. So the first thing we need to talk about is our slope, right, which is our y prime, okay, and that is the value at this certain point, xn, yn. So we're going to plug in the certain values to figure out what that y prime is, okay, and it passes through the point x sub n, y sub n, okay. We're going to need to talk about this h. Okay, this h value is our delta x, okay, so that change in x. We're going to have a delta y, which is going to be our y prime, or our slope, times delta x, or h, okay. We are going to figure out our x value, so to figure out the next x value, we simply take the previous x value and we add that h to it, or that delta x, okay? To figure out the next y value, we're going to take the previous y value and we're going to add that delta y, so that y prime times delta x, okay? And then the last thing we need to talk about is this n. N simply represents the number of steps we're supposed to use to get to our approximation. Okay, so that's kind of the backstory. Now let's get into this first example here, where we're going to use Euler's method to approximate the solution of y prime equaling y squared plus 1, given y1 equals 0, n is 2, which is the number of steps we're going to take, and h, or delta x, is 1/2. So let's kind of zoom in first and list all of the stuff that we know. All right, so we know that y prime is y squared plus 1. We start at the point 1, 0. The number of steps we're taking to get to our approximation is 2, and our h is 1/2, or remember that that is delta x, okay? So what we're going to do is we're going to break down all of our parts, and then I'll kind of explain what this diagram to the right looks like, or what it's talking about, okay? So we're going to have a column that talks about what step we're on, the point we are currently at to help figure out the approximation, okay? We'll talk about what y prime is at that point, okay? And we'll talk about our delta y, which again is that y prime times our h, or delta x, okay? So we're starting initially step 0, all right? Our starting point is 1, 0, okay? So to get to y prime, we're simply going to plug in, oops, let's erase that a second. We're simply going to plug in to this guy here, okay? So we plug 1 in for x, there is no x, so we plug in 0 squared plus 1, and we get 1, okay? So then to get our delta y, we take that y prime and we multiply it by our h value, which is 1/2, and we get 1/2. Okay, so then in step 1, to get to our next x value, we're taking this this h value over here and adding it to our x. Okay, so we're going to have 1.5, or let's just say 3/2. Okay, so what we did here was we added h. Okay, so then to get to the y value, we're going to add delta y to 0. So 0 plus 1/2, okay, this guy over here plus this guy over here, we're going to have 1/2 for our y value. Okay, so now to figure out the new y prime, or the new slope at this point, we're going to plug in 1/2 for y, square it, and add 1. And when we do this, we get 5/4. So then to get that new delta y, we take 5/4 and we times it by our h, which is 1/2, and we get 5/8. Okay, so now we're going to add that 5/8 to the 1/2. We're going to add our h to the 3/2 to get our new point in step 2, okay, which is the final step. So 3/2 plus 1/2 gets us our 2 for x. 1/2 plus 5/8 gets us to 9/8 for our y value. So the way we can conclude this problem is our solution when x equals 2, because that's what we got here, is our y value equals 9/8. So this is the true solution. 9/8 is the approximation when x equals 2. Okay, so we're using these linear approximations. If you take a look, all of these values that we found, so our step 0 is this a over in our diagram. Our step 1 is that point B, and then finally step 2 is our point C on this graph over here. So you can see it's not obviously right on our original graph, but we're just using these linear approximations to approximate the y value at a certain x value. Okay? Okay, so there's kind of the picture as a whole. All right, so in this second example, we're going to look at, well, what if we increase the steps, right? What if we increase the number of approximations we're doing? Are we going to be more accurate? Okay, so let's take a look at this next example. Now, y prime is y squared. We're starting at the point 0, 1/2. We want 5 steps, and our delta x, or our h value, is 0.2. Okay, now I'll kind of go through these calculations. It's going to get kind of nasty, but you can follow along. Okay, so we'll start with kind of setting up our diagram, our steps, right? The point at which we're working. We'll talk about our delta y, which equals y squared, or not our delta y, I'm sorry, our y prime. And then our delta y, which is our y prime times our h value. So the first step, we are at the point 0, 1/2 again. Okay, so what's y prime going to be? Well, we should recognize that y prime is 1/2 squared, which is 1/4. So then we're going to take that y prime, 1/4, times it by our h value, which is 0.2. Okay, and we get 0.05. Okay, so now step 1, our x value just goes up by 0.2, so we are now at 0.2. Our y value is 1/2 plus 0.05, so we're at 0.55. Okay, so now to get to our y prime for the next guy, we're going to take 0.55 and square it, and we get 0.3025. Okay, so 0.3025 times our 0.2 is going to get us 0.0605, and now we can figure out our next point. So step 2, our x value is at 0.4 because we're adding 0.2, and then we take 0.55 plus 0.0605, and now we are at 0.6105. Okay, so now we take that 0.6105, square it, and this is where it's starting to get nasty. This gets us to 0.3727, on and on. So now we take that 0.3727 and multiply that by 0.2, and we end up with 0.0745, continuing on. So as you can see, it's getting nastier. So step 3, our x value is now at 0.6. Okay, our y value is going to be 0.6105 plus that 0.0745, etc., and we get 0.6850. And what we want to do at this point is let's store that value as a, all right, because we're going to be doing some other calculations. So now we take that a value and square it, and when we do that, we get about 0.4692, etc. So 0.4692 times 0.2 is going to get us 0.0938, on and on. So now our next step, as you can see, it's getting nasty. Our x value is 0.8. Our y value, now we're going to take that a value and add this new delta y to it to get 0.7788, etc. So now let's store that guy as b. Okay, so to get y prime, we're taking b squared, and when we square that, we get 0.60668, on and on. So 0.60668 times 0.2 is going to get us about 0.1213. And now our final step. So step number 5, that gets us to an x value of 1. And our final approximation for y is that b value plus that 0.1213, etc. And so we get 0.90023, continuing. Okay, so our approximation, the way we would state it is our solution when x equals 1 is y equals 0.90023. Okay, so as you can see, with more steps, we're staying closer and closer to our actual curve. Okay, so we can use that just as an approximation. Okay, all right, so if you have questions on this, we can certainly go over it tomorrow. Let's move on to the next. Okay, so now we'll get into section 2, which is differential equations, focusing on growth and decay. So we're going to start by deriving the formula. All right, so let's look at the growth rate of population is proportional, all right, to the population size. Okay, so when I see growth rate, we should be thinking y prime, okay, is equal to that proportional, just talks about a constant, a proportionality constant, and the population size. So growth rate of population proportional to population size. So that's just going to be y. Okay? All right, so another way we could think about this, instead of y prime, we can say, well, that's dy dt, okay, equals this k times y. So now let's just solve for what y is, okay? So we know that dy dt, if we were to multiply both sides by dt and divide both sides by y, we really have y is equal to dy over y, or the integral of dy over y is equal to the integral of k dt, okay? So if we keep moving on, we could go ahead and integrate both sides, and when we integrate that left side, we've got ln of y equals kt plus c, okay? So raising both sides, or e to both sides, right, we have y is equal to e to the kt plus c, or another way we could write this is y is equal to e to the c times e to the kt, okay? All right, we'll come back to that. We're going to use that fact in a second, and actually another way we could think about this is this guy here will eventually represent just a constant, right? So we could think about it as y is equal to c, some constant, times e to the kt. That's probably more of what we'll be dealing with, okay? So now let's put this to this first example, well, this last example, I should say. So my tax refund dissipates, goes down at a rate proportional to the amount remaining, okay? So the tax refund dissipates at a rate proportional to the amount remaining. So that should tell us we are using the formula that we derived up above, okay? So we are looking at this y is equal to c times e to the kt, okay? Now, if 20% is spent after 3 months, when will 95% be spent? Well, let's just suppose we're starting at 100%, right? So our starting point is 0, 100. Okay? So let's find our C value, okay? Which should be pretty easy to find. So we're plugging 100 in for y equals C times e to the k and 0 in for t, and we should get C to be 100. Okay, but now we need that k value, right? So we're going to use this next portion here, 20% after 3 months, okay? So right now we're at the point y equals 100 e to the kt. All right, so now we're going to use, all right, well, if 20% is spent, right, after 3 months, so x is 3, how much do we have remaining? 80%, right? So we're going to use that point to find our k value. So 80 equals 100, e to the k times 3, all right, or simply 4/5 equals e to the 3k. And so now we can solve for k. All right, so when we solve, we're going to get 3k is equal to ln of 4/5, taking the ln of both sides. So k is equal to ln of 4/5 all over 3. Okay, so what we want to do now is help ourselves out, we're going to have to store on our calculator. Okay, so let's store e to the k. So we have this k value up here. So e to that k value, let's store that as b. Okay, so plug that into your calculator. So what you should get is b is approximately 0.9283. Okay, so we're going to store this value. Okay, so what we're really dealing with then, I'm going to move up over here, is now we're at the point where we have y equals c times e to the kt. Well, we just stored this portion, right, as b. So what we're really looking at is y equals, c was 100, and it's this b to the t value now. Okay. So now what we want to find is we want to know, well, what's t when we have 5% left, right? We spent 95%. Okay, so now we can certainly do that. So 5 is equal to 100 b to the t, divide by 100, 1 over 20 is equal to b to the t, ln both sides. All right, so ln of 1 over 20 equals t ln of b. All right, so t is equal to ln of 1 over 20 over ln of our b value that we stored. So we should find t to be approximately 40.275 months if you plug that in. Okay, so it takes just over 3.5 years to spend 95% of that refund. Okay, so we'll get more into the growth and decay aspects tomorrow. All right, have a good night. Bye.